Welcome to a small discussion about one of the most elusive hypothetical objects in the universe, a primordial black hole.
Primordial black holes are special in the sense that they could really only form within the first second or so after the Big Bang. That's because at this time period, the universe wasn't homogeneous. There were areas that were a lot hotter and a lot denser than other areas. And the universe today may seem like isn't homogeneous. You look out and you see areas where there are stars and galaxies and regions where there aren't stars and galaxies. If you zoom out far enough to about 600 megaparsecs, the universe is actually quite uniform. These dense areas of the early universe held the equivalent matter of a modern day galaxy. That much matter was sufficient for that region of space to collapse down and form the primordial black hole.
When we think about black holes, we typically think of stellar mass black holes that form from massive stars many times the size of our own sun going supernova, or the supermassive black holes found in the centers of galaxies. Comparatively, a primordial black hole would be very low in mass. Our sun has a mass of about 1.9 times 10 to the 30th kilograms, and what NASA refers to as a medium-sized stellar mass black hole can be about 20 times that size. When considering a primordial black hole, we're talking about an object of at most only about 200 billion kilograms, not even the mass of our moon. The only conditions that might compress an object of such low mass into a black hole are found in the early universe. This was such a hot, dense, and opaque place that a fluctuation in its density could potentially compress a lower mass like this into a black hole.
Now, to talk about what makes a primordial black hole different than a traditional black hole. We've already addressed one of those, and that being how they're formed. Primordial black holes can be much smaller in radius than a traditional black hole, less than a meter across, in fact. A primordial black hole has much more matter inside of its core, being that it takes about as much matter as what fills up a galaxy to cause that region of space to collapse in the early universe, while a traditional black hole is formed from a collapsing star. And not even all of the stars converted into the black hole, since it goes supernova when it's collapsing and jettisons a bunch of matter away from itself. The other thing is they both can actually gain matter, but their sizes have a much wider range just based on how they're formed. Traditional black holes can't have formed before stars existed because stars are what create them, while a primordial black hole can't have formed since stars existed because at that point the universe was far too homogeneous to allow it to happen.
Now, to get an idea of how to search for these things as well as why searching for them is so difficult to begin with, we have to refer back to Stephen Hawking's work on black holes. Hawking proposed that black holes might evaporate over time via particle-antiparticle pairs blipping into existence near the event horizon of a black hole due to the quantum uncertainty principle. If we think about this in terms of Einstein's famous equation, E equals mc squared, an antiparticle falling into the event horizon of a black hole carries with it negative energy and effectively negative mass, reducing the overall mass of the black hole ever so slightly while the free particle radiates away in the form of an X-ray or gamma ray. This phenomenon is what we now call Hawking radiation, of course, and as it turns out, the relationship between a black hole's mass and its evaporation rate is inversely proportional. That is to say, the smaller the black hole, the faster the evaporation rate. The first problem we're presented with in trying to search for primordial black holes is in fact the relationship between the mass and the evaporation rate being inverse. So let's consider again a primordial black hole of 200 billion kilograms, and also the lifetime of a black hole in a vacuum that isn't accreting mass. That lifetime can roughly be calculated by the equation T equals about 14 billion times the mass of the black hole in grams divided by 1.7 times 10 to the 14th grams cubed. If we calculate the lifetime of a black hole that could have formed within the first second of the Big Bang, one with a mass of at most 200 billion kilograms, we find that its lifetime would be about 22.8 billion years. This means that most of the primordial black holes with masses significantly smaller than 200 billion kilograms would have evaporated away by now, and the ones that are left most likely accreted mass over their lifetime and look like a massive black. Now let's consider the possibility of one that didn't accrete mass. In that case, it could still have upwards of billions of years left in its life, not yet evaporating at a rate we could detect, and on the other hand, a black hole that is evaporating at a rapid rate much closer to the end of its lifetime wouldn't really appear black to us anymore. In Hawking's own words, such holes hardly deserve the epithet black. They really are white hot and emitting energy at a rate of about 10,000 meg. From there, the problem becomes distinguishing them from other sources of gamma and X-rays. Hawking goes on to say, in order to observe a primordial black hole, one would have to detect several gamma ray quanta coming from the same direction within a reasonable space of time, such as a week. Otherwise, they might simply be part of the background. But Planck's quantum principle tells us that each gamma ray quantum has a very high energy because gamma rays have a very high frequency, so it would not take many quanta to radiate even 10,000 megawatts, and to observe these few coming from the distance of Pluto would require larger gamma ray detectors than any that have been constructed so far. Moreover, the detector would have to be in space because gamma rays cannot penetrate. Now, since the time in which Hawking wrote that in A Brief History of Time, we've gone on to develop better instruments. For instance, the Fermi Gamma Ray Space Telescope was launched in 2008 in part to search for primordial black holes through their gamma ray emissions. Unfortunately, as of 2018, Fermi has not yet been successfully used to make an observation of a primordial black hole or hawk. As incredible as it would be to see what a primordial black hole at the end of its life could tell us about the behavior of black holes at that time, the odds of actually observing one, as you can see, are impossibly low. So what other options do we have? We could potentially create a microscopic black hole or something akin to it in a particle accelerator like the Large Hadron Collider. In that way, we could directly observe the decay products of a microscopic black hole as it explodes. But this, unfortunately, has also not been successful yet. So we find ourselves waiting on either an incredibly powerful accelerator to be built or a very lucky astronomer to finally make that observation.